Okay, good morning. So, in the last class, we are discussing about the fast Fourier transform. So, what is the need of the fast Fourier transform? Here, the number of transitions can be reduced when compared with the DFT. So, FFT is fast Fourier transform. Here, the number of transitions will be reduced when compared with the DFT, discrete Fourier transform, right? Okay. Then coming to the classes of the first Fourier transform algorithm, here we have two classes: decimation in time FFT and decimation in frequency FFT. Decimation in time FFT, we are discussing about that. Okay, decimation in time FFT. This is also called as radix 2 DITFFT. Okay, so here it will be divided into even indexed values of x of n and odd indexed values of x of n. Okay, that is, if it is even, then xc of n equal to 2n. If it is odd, then xo of n equal to 2n plus 1 for n equal to 0 to n by 2 minus 1. So, similarly, for odd indexed values also, xo of n equal to 2n plus 1, and where n is 0 to n by 2 minus 1. Okay, so the endpoint DFT can be written as x of k equals sigma n equals 0 to n minus 1, x of n t power minus j 2 pi n k by n, where t power minus j 2 pi by n can be written as wn. Okay, wn power nk. Okay, e power minus j 2 pi by n equal wn, where k is varying from 0 to n minus 1, right? So like that we will write this into combination of even and odd indexed values of x of n. We obtain x of k equals sigma n equals 0 to n minus 1. Okay, x of n into wn power nk plus sigma n equals 0 to n minus 1, x of n into wn power nk, where this x of n is replaced by 2n, and here x of n is replaced by 2n plus 1, so that it will become xe of sigma n equal to 0 to n by 2 minus 1, xe of n into wn by 2 of power nk plus wn power k into sigma n equal to 0 to n by 2 minus 1, xo of n into wn by 2 power n by k. So this is called n by 2 point DFT of even indexed sequence, and this is n by 2 point DFT of odd indexed sequence, right? Like this, we will write the DFT as even indexed sequence and odd indexed sequence, but n by 2 point. Okay, so done the whole, we can write x of k equal to xc of k plus wn power k into xo of k, right? For k is greater than, this is even symmetry. So for k is greater than or equal to n by 2, then wn power k plus n by 2 is equal to minus wn power k, or we can write this as mm, x of k equal to xc of k minus n by 2 minus wn power k minus n by 2 into xo of k by k minus n by 2. So this is equation number 9. So for direct evaluation of DFT, let us take n is 8, then it can be divided into even indexed values and odd indexed values. So n by 2, that is 8 by 2, that is 4. So when n equal to 0, xc of n is 2n, and n equal to 0, xc of x naught of n equal to 2n plus 1. Like that, we will get 4 values for even values and 4 values for odd values. So for even values, it will become 0 to 4 6. For odd values, it will become 1 3 5 7. Right? So we will substitute these values in equations 10 and 11. 10 and 11, we will get the expressions like this: x of 0 is equal to xc of 0 plus w8 for 0 into xo of 0. Similarly, x of 1 equal to xc of 1, okay, plus w8 for 1 into xo of 1. Similarly, x of 2 equal to xc of 2 plus w8 for 2 into xo of 2. X of 3 equal to xc of 3 plus xo of 3, right? Similarly, we'll substitute these values k equal to 4 to 7 values in equation number 11. Okay, so that we will get x of 4, x of 5, x of 6, and x of 7 values, right? Like this. Okay, so that from that expressions we can we can draw the butterfly diagram like this. A value is xe of 0, b value is xo of 0, and this resultant will be a plus w840 into b, that is xe of 0 plus w840 into xo of 0, right? Right. So in the same manner, this will be written as a minus w840 into b. Okay, depending on the arrow mark. If the arrow mark is goes at here, if the arrow mark is goes here, then we will add these two components, add these two elements, xe of 0 plus this weight into w840 into xo of 0, right? Similarly, if it is like this, arrow mark will come at here. So then it will be written as a minus w840 into b, that is xe of 0 minus w840 into xo of 0, right? Right. So with this we can draw the butterfly diagram. Now the values of x of k for k equal to 0, 1, 2, 3, 4, 5, 6, 7 can be obtained. Okay, so suppose for example, if we take 8 point DFT, okay, 8 point DFT, here n equal to 8, so it can be divided into n by 2, that is 4 point DFT. So we will combine, it will be decomposed as two 4 point DFTs, and it will be combined, so that we can draw the butterfly diagram like this. So this is xe of 0, xe of 1, xe of 2, xe of 3 with 4 inputs. For this 4 point DFT having these 4 inputs, and this is again another 4 point DFT with inputs xo of 1, xo of 2, xo of 3, and xo of 4, right? Right. So with this 4 points, right. So this is x of 0, this is x of 2, this is x of 4, x of 6, this is x of 1, x of 3, x of 5, and x of 7. With this we can take the weights w840, w841, w842, w843. How to get this x of 0? This is xe of 0 plus w840 into xo of 0. Similarly, x of 1 is xe of 1 plus w841 into xo of 1. X of 2 is xe of 2 plus w842 into xo of 2. Similarly, x of 3 is xe of 3 plus w843 into xo of 3. Similarly, how to get these core values x of 4, x of 5, x of 6, and x of 10? X of 4 is xe of 0 minus w840 into xo of 0. X of 5 is xe of 1 minus w841 into xo of 1. And x of 6 is obtained by xe of 2 minus w842 into xo of 2. Similarly, x of 7 is obtained by xe of 3 minus w843 into xo of 3, right? Like this we can find these 8 values, right? Okay, so the sequence x of n is shuffled into even indexed sequence xe of n and odd indexed sequence xe x naught of n. The inputs to the butterfly is separated by n by 2 samples, that is 4 samples. So the n by 2 point DFTs can be expressed as combination of n by 4 point DFTs. Okay, xe of k for 0 is less than or equal to k is less than or equal to n by 2 minus 1 can be written as c. Xe of k is equal to xe of k plus wn for 2k into xeo of k for 0 is less than k is less than or equal to n by 4 minus 1, that is 0, 1, 0 to 1 for two values. For two values, this one. For another two values, 2 and 3. So it can be written as xe of k minus n by 4 minus wn for 2 into k minus n by 4 into xe of xeo into k minus n by 4 for n by 4 is less than or equal to k is less than or equal to n by 2 minus 1. By doing a problem on problem, we can understand this concept. Okay, uh, this is the analysis of how to do this 8 point the 8-point sequence using butterfly model. Okay, so this xe of k is n by 4 point DFT of even numbers, and xeo of k is n by 4 point DFT of odd numbers. In the same way, x naught of k, xo of k is O of k plus Wn power 2k into x O ok for 0 is less than or equal to k is less than or equal to n by 4 minus 1, and xo of k equal to xeo of k minus n by 4 minus Wn power 2 into k minus n by 4 into xo of k minus n by 4 for n by 4 is less than or equal to k is less than or equal to n by 2 minus 1. That is equation number 13. So xoe of k is n by 4 point DFT for even numbers, x over of k is n by 4 point DFT for odd numbers. Whereas for this one, xe of k, xe of this is xe of 0, this is 4 point, this is 4 point DFT, this is 2 point DFT. Remember, this is 2 point DFT. That's why it is combination of XE of k plus XEO of k. XE of k minus n by 4 minus XEO of k minus n by 4 for even numbers. Okay, this is n by 4 point. If n is 4, that is 4 by 4, 1 point DFT, right? So if it is n by 2, that is 8 by 2, that is 4 point DFT, right? Like this, it can be divided for even sequence, even indexed sequence and odd indexed sequence. Okay, suppose if we take for n equal to 8, xe of n is divided into even and odd indexed sequences are as xe of 0 is equal to xe of 0, xeu of 0 is xe of 1, xe of 1 is xe of 2, and xe0 of 1 is xe of 3. So this is n by 4, n by 4 indexed, n by 4 indexed. So now from equation number 12, we have xc of 0 is equal to xc of 0 plus W840 into xco of 0. Similarly, xc of 1 equal to xc of 1 plus W842 into xco of 1. Similarly, xc of 3 equal to xc of 0 minus W840 into xc of 0, xco of 0, and xc of 3 equal to xc of 1 minus W842 into xu of 1. This is a combination of n by 2 and n by 4 indexed sequences. Similarly, it is 2 point DFT. So xe of k is 2 point DFT, whereas xe of k is 4 point DFT. Remember, so xe of k is 2 point DFT of even numbers of xe of n, and xu of k is 2 point DFT of odd numbers of xe of n. Similarly, xo of n can be divided into even and odd numbered sequences like this, like equation number 14. We will get equation number 15 also. So where x OE of k is 2 point DFT of even numbers of xo of n, and xo of k is 2 point DFT of odd numbers of xo of n. Construction of 8 point DFT from 2 4 point DFTs and 4 point DFTs from 2 point DFTs is like this. See here, these are 2 point DFTs. Initially, these are 2 point DFTs. This will be given to the 4 point DFTs. These combination of 4 point DFTs is this is 8 point DFT. Okay, 8 point DFT. So initially we'll take 4 2 point DFTs. Okay, 4 2 point DFTs. So this is a 2 point DFT 1 2 3 4. Okay, these outputs are connected to 4 points, 4 point DFTs, and these 4 point outputs, these 4 point outputs are given to the 8 point DFT. Okay, so this is XE of 0, XE of 1. Next, XEO of 0, XEO of 1, XO of 0, XOE of 1, XO of 2, and XO of 0, XO of 1. So these will be given to the XE of 0, XE of 1, XE of 2, XE of 3, XO of XO of 0, XO of 2, XO of 1, XO of 2, XO of 3, multiplied with these weighing factors W8 for 0, W8 for 1, W8 for 2, and W8 for 2, so that we will get the 8 point DFT like this. XO X of 0, X of 1, X of 2, X of 3, similarly X of 4, X of 5, X of 6, and X of 7. Right? So in this figure, the input sequence is again reordered. The input samples in each butterfly are separated by n by 4 samples, that is 2 samples, and there are 2 sets of butterflies. In each set of butterflies, the twiddle factor exponents are same, and separated by 2. So flow graph of decimation in time algorithm is like this. Okay, W8 for 0, W8 for 0, W8 for 0, W8 for 0. Here W8 for 0, W8 for 2, W8 for 0, W8 for 2. Okay, now here it is W8 for 0, W8 for 1, W8 for 2, W8 for 2. Right? So finally we will get the result x of 0, x of 1, x of 2, x of 3, x of 4. So here these inputs are reordered as x of 0, x of 4, x of 3, x of 6. This is even numbers. And here x of 1, x of 3, x of 5, and x of these are odd numbers. Okay. This algorithm has been called decimation in time since at each state the input sequence is divided into smaller sequences. That is, the input sequence are decimated at each state. That's why this is called decimation in time. From the flow graph, several important observations we have to observe the several important observations. These are, suppose here the input samples index is like this 0 to 7. So we will take the binary representation of this input samples. So 0 0 0 0 0 1 0 1 0 0 1 1. Okay, 4 1 0 0 1 0 1 1 1 0 and 1 1 1. Now in the next step we will take the bit reversal binary. Bit reversal binary means one bit it will be reversed. So 0 0 0. This is 1 0 0. This is 1 0 0 1. Then 1 1 0. This is 0 0 1. This is 1 0 1. Then this is 0 1 1 0. Bit reversal. 0 0 1. And this is also 1 1. Bit reversal sample index. So 0 0 0 is 0, 1 1 0 0 is 4. This is 0 1 0 2, 1 1 0 6, 0 0 1 1, 1 0 1 1 0 1 5. Okay, this is 0 0 0 1 1, that is 3, 1 1 1 7, 1 5 3 7. These are the taken at the input levels. So how to get these values 0 0 4 2 6. So by using this bit reversal binary, bit reversal sample index 0 4 2 6 1 5 3 7 will be written at here. Okay, like this. Okay, comparison of number of multiplication for the direct evaluation of DFT versus FFT algorithm. Now we will compare DFT versus FFT algorithm. Number of multiplication for the index. If we take number of multiplication is n square for DFT, whereas for FFT this is n by 2 log n to the base 2. Okay, n by 2 log n to the base 2. We will compare these two. So number of transactions will be reduced. Okay, so number of stages. Suppose if we take these are the number of stages. 2 stage, 3 stage, 4 stage, 5 stage, 6 stage, 7 stage, 8 stage, 9 stage, 10 stage, like this. So number of points, that is n. So n can be represented as 2 power number of stages, 2 power n. So 2 power m means 2 power 2, that is 4, 2 power 3, that is 8, 2 power 4, 16, like this. Okay, these are the number of points denoted as capital N. Now we will take the number of complex multiplications using direct evaluation and in FFT algorithm, that is n by 2 log n by 2. In direct evaluation, that is n square. So here n is 4, n square is 16. It is 8, 64, 16 to 56, like this. So FFT algorithm, it will become n by 2 log n to the base 2. So n by 2, n is 4, 4 by 2, 4 by 2 log n to the base 2, log 4 to the base 2. Okay, so that it will become 4, it will become 12, like this. So the speed improvement factor, now we can find out the speed improvement factor, that is n square by this DFT direct evaluation, n square by n by 2 log n to the base 2. So this is 4, this is the speed improvement factor, this is 5.5, like this. So the summary of the steps of radix to DITFFT algorithm. So the number of input samples n equal to 2 power m, where n is integer. The input sequence is shuffled through bit reversal process. Okay, the number of stages in the flow graph is given by m equal to log n to the base 2. Each stage consisting of n by 2 butterflies. Inputs and outputs for each butterfly are separated by 2 power m minus 1 samples, where m stage index, that is first stage m equal to 1 and second stage m equal to 2 and so on. The number of complex multiplication is given by n by 2 log n to the base 2, whereas the complex multiplication in DFT is n square. Okay. Okay, the number of complex additions is given by n log n to the base 2. Okay, so the Twiddle factor exponents are a function of a stage index m and is given by k equal to nt by 2 power m, where t is varying from 0, 1 to up to 2 power m minus 1 minus 1. Next, the number of sets or sections of butterflies in each stage is given by the formula 2 power m minus m. The exponent repeat factor ERF, that is called ERF, which is the number of times the exponent sequence associated with the n is repeat, is given by 2 power m minus small m. 2 power m minus small m. The exponent repeat factor ERF, which is the number of times the exponent sequence associated with m is repeat, is given by 2 power m minus m. Okay. So now we will draw the flow graph of 16-point decimation in time FFT. The flow graph of 16-point n is 16. Okay. So here we are using the following steps. N is 16. The input sequence is shuffled through the bit reversal index. So here, first of all, we will take 0 to 15 numbers. So we'll write the binary representation 2 power 4, that is 16. Okay. So binary representation, 4-bit binary representation, will write the bit reversal order. Okay. 110000101010, then 0110 1110 0001 1010 0101 1101 0011 1011 0 0 111. Okay, 0 111, then 111, right? So these bits will become 0 8 4 12 2 10 6 14 for even numbers, 1 9 5 13 3 11 7 15 for odd numbers. Okay, so this is the order. Okay, now third stage, number of stages m equal to log 16 to the 2 is forced 4, or m equal to log 8 to the 2, that is 3. Okay, number of butterflies per stage is n by 2, that is 16 by 2 equal to 8. Okay, next 16 by 4, that is 4. Okay, the inputs out for each butterfly in each stage is separated by 2 power m minus 1 sample. Stage 1 for each butterfly separated by 1 sample, and stage 2 input outputs for each butterfly are separated by 2 samples. Okay, 1 2 4, like this. 2 power m minus 1 equal to 2 power 1 minus 1, that is 1. 2 power m minus 1 is 2 power 2 minus 1, that is 2. 2 power 3 minus 1, that is 4. Okay. Okay, stage 3. Coming to the stage 3, outputs for each butterfly are separated by 4 samples, and stage 4 inputs or outputs for each butterfly are separated by 8 samples, that is last stage. The number of complex multiplication is given by n by 2 log n by 2 log n to the base 2, that is 8 log 16 to the base 2, that is 32. Okay, the number of complex additions is given by n log n to the base 2, that is 64. Okay. Okay. Next, the number of sets or sections of butterflies in each stage is given by 2 power m minus m. M minus m. For stage 1, the number of sets of butterflies are 2 power 4 minus 1, that is 8. And for stage 2, 2 power 4 minus 2, 4. And for stage 3, 2 power 4 minus 3, 2. And for stage 4, there is only one set of butterflies. Okay. Fiddle factor components for each stage are given by k equal to nt by 2 power m, where t is varying from 0 to 2 power m minus 1 minus 1. For stage 1, the exponent is 0. For stage 2, the exponent is 0, 4. For stage 3, the exponents are 0 to 4, 6. And for stage 4, the exponents are 0, 1, 2, 3, 4, 5, 6, 7. That depends upon this formula. So the exponent repeat factor ERF, which is the number of times the exponent sequence associated with m is repeat is given by 2 power m minus m. That is for stage 1 ERF is the exponent repeat factor is 8, for stage 2 ERF is 4, for stage 3 ERF is 2, and for stage 4 ERF is 1. From the steps 8, 9, 10. From the steps 8, 9, and 10, we can draw the following conclusions. For stage 1, schedule factor exponent is 0 and is repeated 8 times. All the 8 sets of butterflies have schedule factors of W16 power 0. For stage 2, W16 power 0 and 4. Okay. And for stage 3, W16 power 0, W16 power 2, W16 power 4, and W16 power 6. Okay. And last stage fiddle factors are W16 power 0, W16 power 1, 2, 3, 4, 5, 6, 7. See here. So for stage 1, these are the bit reversal indexes. Bit reversal index is based on the bit reversal indexes. For stage 1, W16 power 0 fiddle factor. So this is these are the this is stage 2 inputs. So here W16 power 0, W16 power 4. This is W16 power 0, 2, 4, 6. And here W16 power 0, 1, 2, 3, 4, 5, 6, 7. So finally we will get the result like this 16 power 16 FFT output. So here we have 4 stages. Okay. Okay. Now we will do a problem. So let us take this problem. Compute 4-point DFT of the sequence x of n equal 0, 1, 2, 3 using decimation in time FFT. Okay, fiddle factor associated with the butterflies are W440 equal to 1, W441 equal to e4 minus j 2 pi by n, that is e4 minus j pi by 2. Okay, whereas the formula is Wn power k equal to e4 minus j 2 pi by n. Okay, so by using this formula, we can find out this e4 minus j2 pi by 2 is cos pi by 2 minus j sin pi by 2, it is minus j. Okay, so using bit reversal index, we can write this index 0 to 13, 0 to 13. Okay, so initially W440 and W440. Okay, so W440 is 0 plus W440 into 2, that is 0 plus 2. So this is 0 minus W440 into 2. Okay, so that is minus 2. Here also it is 1 plus 1 into 3, that is 4. 1 minus 1 into W into 3, that is minus 2, right? So here it is W440 and W441. Okay, so it is minus j. W441 is minus j, right? So it is simply x of 0 equal to x of 0 is 2 plus 1 into minus 2 plus this 2 here is minus 2, this is 4, 2 plus 4 into W440 into 4. Okay, so W2 plus 4 6, this is 6. How to get this one? This is minus 2 minus 2 my plus w4 for 1 into minus 2. Okay, x of 1. W4 for minus 1 minus j. So this is minus 2 minus j into minus 2 minus j into minus plus. So it is minus 2 plus 2j, right? This value. Next one, like this, we can calculate the all these values. Okay, so x of finally x of j is 6 minus 2 plus 2j minus 2 and minus 2 minus 2j. Like this, we can calculate these values. So next we will do the next problem. Compute 8-point DFT of sequence x of n equal to 1 for 0 is less than or equal to n is less than or equal to 7 and is 0 otherwise using decimation in time effective. The hidden factor associated with bacteria can be found as okay, by simply calculating this w n k equal to e power minus 2 pi by n, e power minus 2 pi by n, e power minus j 2 pi by n. By simply calculating this values, we can get w for 0 is 1, w for 1 is 0.707 minus j 0.707. Okay, w for 2 is minus j, w for 3 is minus 0.707 minus j 0.707. Okay, okay. So using bit reversal, you can get these values 0.4261537. Okay, 0.4261537. W for 0, W for 0, W for 2. Okay, 8 become 8 9. Okay, W for 0, W for 2. Then it is W for 0, 1. 2. Okay, like the above one. Okay, like this, we can draw the butterfly diagram. We can draw the butterfly diagram. Okay, W equal 0, then W equal 2. So here already these values are given. X of n is given as 1. From 0 is less than or equal to n is less than or equal to 7. So for all values, x of n value is 1 only. Okay, so all are ones. So S1, S2, S3 outputs are like this. All are ones. So you can calculate the values as x of t equal to 8, remaining all zeros. The butterfly shown in figure is decimation in time FFT with n equal to 32. Assume that 5 stages of the butterfly diagram are indexed by m equal to 1 to 5. What are the possible values of k for each of the 5 stages? So these are like this. K equal to n by 2 power m. So for stage 1 m equal to 1, t equal to 0, that is k equal to 32 into t 0 by 2 power 1. So k is 0. For stage 2, m is 2, t 0 comma 1. So it is 0 8. For stage 3, m is 3, t 0 1 2 3. Like this, we can calculate the values. So like this, you can find the values. So the problem. We done these problems. 8 find here with the find by values. These are the given inputs. Time FFT. Decimation in time FFT. Okay. This is about the decimation in time. Next one is decimation in frequency algorithm. Decimation in frequency algorithm. Okay, we will continue this in the next class. So far we discussed about the decimation in time DITFFT, and we'll see some problems also. So you will solve the problems manually. So take the material. So follow the material and do the problems. Okay. Follow the material and do the same problems. Practice it. Okay. So in the next class we will discuss about the decimation frequency algorithm, that is DIFFT. Okay. With this I am closing the today's session. Tomorrow we will continue the decimation frequency algorithm, DITFFT. Okay. Thank you.